Welcome to a lesson with Dr. Powell. Let's take a look at a proof for why the radical of an ideal in a commutative ring R is equal to the intersection of the prime ideals that contain that ideal. So the ideal that we're going to be thinking of is A, and its radical is notated like this, square root of A, and the radical of A is defined to be the ideal of all elements such that a power of that element is going to be in our original ideal here, like A. Okay, so that's one way we can describe what a radical ideal is. So let's get to work. First of all, if an element is in the radical of A, then there's some power that's in A, and let's suppose that this P right here is a prime ideal that contains A. So in particular, A to the M, so this little a to the M is going to be contained in here, in this prime ideal. Um, Now, by the definition of what a prime ideal is, you could split this up into like, if you want, you can do A and AM minus 1, and either A or AM to the minus 1 is in the prime ideal. And then if it's A, then what we've just shown is that A is contained in the prime ideal. If it's A to the M minus 1, then you can keep on, then you could repeat this idea over and over again until you just get to A. And in the end, we get that if A is in this radical, A is actually in the, so this is little a, is contained in the prime ideal that we said was containing our original ideal, capital A. Okay, so essentially what we have is as the radical is contained in all prime ideals that contain the original ideal. So we know that we have this containment, that the radical of A is contained in here. So the only thing that we really need for equality is to think about, well, what if something's, so we know this is contained in there. What if we have something extra? Um, what if this is a little bit bigger? All right. So let's suppose we have some element X, which is in the intersection, but not in the radical. So we're going to write down some canonical maps. This is a quotient map. We're quotienting, so we have a ring and we're quotienting out by the radical of A, of capital A. And then this right here is just the canonical map a from a ring to its localization at an element. So here localization X, so X will now be a unit over here in this ring. Now, okay, so, well, what we will do is in this ring right here, let's take a maximal ideal. And we know that all rings uh, admit a maximal ideal. Um, so if you look at all this, so if you look at the set of all proper ideals or ideals that are not equal to the whole ring, um, that's a non-empty collection, specifically because the zero ideal is uh, if this is not if this is a ring that has identity in it, which it is, and which is not zero, then the zero ideal is in that collection. And then using Zorn's lemma and chains and union of a chain is an upper bound for that chain. So you end up getting, yes, there exists such a maximal ideal, and maximal ideals are prime. And the preimage of a prime ideal via a ring homomorphism is again prime. So we have a prime ideal over here, and this prime ideal does not contain X, specifically because this ideal doesn't contain X. I mean, if it did, I mean, X is a unit over here, and so you actually get the whole ring, and it wouldn't be maximal anymore. It wouldn't be a proper ideal. And if X was in this guy over here, it's sent over to, then that would make X over here and would create a problem. So we know for sure that this ideal, this prime ideal, does not contain X. Well, wait a minute. This is a prime ideal, but we know that, okay, so So what do we know here? We know x is not contained in here, but we were assuming right here that x was actually contained in all primes that contain a. Mm, okay, and a prime and an ideal over here, actually, all ideals over here actually contain the radical of a, which contains a itself. So that's a problem here if we say that x can't be in there because we're assuming that x is in all prime ideals. So that's our contradiction. So we've contradicted this fact, so we actually have equality, and that concludes this little proof. Thanks for watching.